Francisco. Okay, yeah. Let me first initiate the YouTube stream.
You can give it a minute and then start maybe, but yeah.
Hello everyone, and welcome to today's Games, Decisions and Network seminar. It is my pleasure to introduce you our speaker, Naomi Leonard. She is Edwin Wilson Professor of Mechanical and Aerospace Engineering and Associated Faculty in Applied and Computational Mathematics at Princeton University. She received her BSc in Mechanical Engineering from Princeton University and her PhD in Electrical Engineering from the University of Maryland. She is a fellow of the American Academy of Arts and Sciences, SIAM, IEEE, IFAC, and ISME, and a MacArthur Fellow. Her current research focuses on dynamics and control of multi-agent systems on networks with application to distributed decision-making, spreading processes, multi-robot teams, and collective behavior. We are delighted to have you as our speaker, Naomi. Thank you. Thanks for joining us. And before we start, I want to make a very brief announcement to our audience. As usual, this talk will be recorded and streamed on YouTube, and we will have a Q&A at the end of the talk. Thank you very much. Okay, you can start.
Great, thanks very much. I'm going to talk about some new work on thinking about how we use a model that we've presented recently on opinion dynamics. It's a nonlinear opinion dynamics model that models the dynamics of many agents making opinions, forming opinions continuously over time, real valued opinions of multiple options. And the idea here is to think about this nonlinear opinion dynamics model as a multi-agent reinforcement learning model in the context of finite games, so multi-agent strategic settings. And I think there's really interesting possibilities. The nonlinear opinion dynamics introduces the possibility of not only looking at multi-stability of solutions, which is already kind of interesting in these settings where there can be different kinds of possibilities for convergent behaviors in games, but also if we leverage some homogeneity, we can get a really good handle, meaning analytic tractability on these dynamics. So on how solutions change as a function of parameters, which makes it all the more sort of useful to try to understand from a principled perspective, how these dynamics play into games. And I think that sort of the basic idea is that we're introducing the opportunity possibly for there to be some exchange of opinions among players over the course of this sort of repeated game in continuous time, and what influence that has on what happens. So this, the nonlinear opinion dynamic model is something that I've been working on with my PhD student, Anastasia Biziaeva, and my longtime collaborator, Alessio Franchi. And newer ideas about interpreting this in the context of games is joint work with Shinkyu Park, who has been a postdoc in my group and is now a new assistant professor at KAUST, as well as a PhD student, Wenshu Zhu. Let's see. Okay, so let me just start with some definitions. So we're talking in this context about multi-agent finite games. So there are NA agents or players, and each agent has a set of actions or strategies. Let's say that there's n sub O of those strategies. And so a mixed strategy for agent I would be defined as a probability distribution over those actions or strategies. So xi1 through xi n sub O. And these would live, this vector lives in the simplex. So these are all probabilities, they sum to 1. And so then the mixed strategy profile of the set of agents would be the vector living on NA copies of the simplex, each agent's probability distribution over their actions. And then we can define the payoff to agent I for selecting strategy J as capital U sub ij, which can depend upon all of the probability distributions of all of the players. So this is where we get our multi-agent interaction. So then the expected payoff to agent I for its mixed strategy looks like the sum of xij, which is its probability of playing strategy J, and then the expected payoff for playing strategy J summed over all the strategies. Okay, so I'm going to basically build on what's known as the exponentially discounted reinforcement learning approach. This is a score-based reinforcement learning approach modeled in continuous time and applied to these finite games. So the idea in continuous time means that you're playing the game indefinitely and with an infinitesimal time step every time you play the game. So essentially in continuous time. So here are the papers where this was introduced, and I'm going to sort of follow along with the paper by Gao at Pavel, who builds on the frameworks of these other papers. So this is a sort of a 3-stage process. And so in the first stage, it's called the assessment stage. Each agent I keeps a score, and I'll just call it this vector zi hat. So each element is a score, so just a number, a real number that it gives, agent I gives to each of the strategies based on its received payoff. Okay, so the dynamic that we see in these models, which is essentially this exponentially discounted reinforcement learning model, looks like this, right? So here is the rate of change of agent I's score of strategy J. Here's the discount D, and this is the reward IJ. So that would be the reward received at time T, given everybody else's strategies, minus its score, right? So we just have this exponential evolution of this score chasing the reward that it's received. So D is like a learning rate. The initial condition you can think of as like an initial bias. So Zij at time 0 would be its initial bias, agent I's initial bias towards, I should say, strategy J. So the second stage is the choice stage. So each agent maps its score, so its vector where it's given a score to every strategy onto a mixed strategy. And there's a lot of possibilities. So this is sort of like best response. One can simply be a softmax. So this is just the softmax with temperature eta. And so this gives us a distribution of probabilities over all the strategies. And so then the next stage is essentially to play the game according to the agent I will play the game according to its mixed strategy. Every agent will play this game, and this is where we'll have the interaction. And then essentially you just keep going back and repeating indefinitely with this infinitesimal time step. Okay, so here's a picture from Gao and Pavel where they show this as a sort of feedback loop, right? So this is this first stage where you exponentially discount. So you come up with this score based on your reward for every agent does this for every strategy, right? Out come the scores from all the different agents. We have the softmax choice map, which gives us our mixed strategies. We play the game and the payoff function gives us a reward, and we just continue along indefinitely. Okay, so here's our idea. It's just merely adding a little bit of feedback on the communicated opinions or scores. So here's where we're going to start thinking about opinions. if you think about those scores, those are your opinions. And agent I's opinion about option J, you can think about as agent I's score about strategy J, you can think about as an opinion about option J. Okay, and so, but we're imagining now that it's possible that these agents can have some talk or some communication over a network with the others. So you would at least perhaps get a measurement, an observation of your neighbor's opinions. And you can feed that back. And what we do is we feed that back through a saturation function. Right, this is where we introduce a nonlinearity. So basically, for small opinions, they register as those small opinions, but as they get really, really large or really, negative, they saturate smoothly, and those get fed back. So this is the only difference in what we just saw in the exponentially discounted reinforcement learning. Now we're just feeding back through saturation function opinions. And that's our opinion dynamic model. So you can think about this integration or this interpretation of opinion dynamics model as kind of an extension of this exponentially discounted reinforcement learning model for multi-agent finite games with this additional exchange of opinions. Okay, so let me tell you a little bit more about this opinion dynamic model before I show you what kinds of opportunities this introduces in the context of our games. So in the opinion dynamics model, again, we think about NA players or NA agents, 1 through NA, and those strategies or actions, we call them options. And so we have NO of them, just as I introduced. And again, the agent I has an opinion of each option or strategy, and we call that ZI hat, which can just be a real number. The higher that number, just like if it's a score, the better, the higher opinion the agent has about that option. We work with relative opinions. So agent I has a relative opinion of each option J. That's just simply, we remove the hat. So ZIJ is ZIJ hat minus the sum over all the options. That gives us this opinion relative to all the other opinions. So still, the higher ZIJ, the better you feel about this option relative to the other ones. Okay, so that's opinions. Then I'm going to make some other definitions about weights on information that's being exchanged between agents or even within an agent. So let's just picture agent I on the left here, agent K on the right. Each one, agent I has an opinion, a relative opinion about option J, option L, option P. Agent K has an opinion about option J, option L, option P. And there's 4 different ways in principle that we could have influence between these different opinions. The first 2 are interagent influences. So this just says A, I, K, J, J. That's the kth agent's opinion of the jth option on the ith agent's opinion of the jth option, right? And so just to make our notation a little easier, let's just call that gamma, right? Let's just say all those weights are equal to gamma. And so then we have interagent different option weights. So agent K's opinion about J could influence agent I's opinion about L. And let's just, for the sake of clarity, call that for any pairs delta. We also can have intra-agent influences. So this is like a self-reinforcing term if it's positive, right? That's agent I's opinion about P on agent I's opinion about P. So I could be kind of sort of snowballing. If I like my opinion, it just could, it get kind of self-reinforced, revved up about it. Let's just call that alpha. We'll think about alpha as being positive for self-reinforcing. And then you could also have your own opinion. So K's opinion on L and how it it's influenced by its own opinion about P, and let's call all of those sorts beta, right? So we can kind of interpret them. So alpha is positive, these are self-reinforcing. If beta is negative, that's mutually exclusive option. So one is, if one becomes favored, it makes the agent disfavor the other ones. We can talk about agents, and this is a little bit different from the standard notion of cooperative and competitive in games, but we'll just call when gamma minus delta is greater than 0 as agents being cooperative. That just means that I'm, following along with my neighbor, as opposed when this is negative, it's a competitive interchange, because then I'm kind of, if you're favoring that option, I'm going to disfavor it. Okay, so with these definitions, we can write down a general model. This is our general model of opinion dynamics. This is sort of, in some sense, that we can actually say rigorously the most general you need to be to get all the kinds of possible behaviors, collective behaviors that can happen in this setting. And so for every agent and every option, we can talk about the rate of change of that agent's opinion about that option. And this is the dynamics are defined by this. We just subtract off, because these guys are written so that they're relative. We subtract off the average of the dynamics for all the other options. But the most important term is looking at these three terms. I can just sort of say up front, this is like, if you ignore this big middle term, this is like the exponentially discounted, if you think about these as rewards, and this is the learning parameter D. That's the old model, and this is all the exchanges with saturation functions that we've talked about introducing. So we can call this damping. We can call this the social influence. We can call this the input. And we have a little gain in front of our social influence, because it sort of matters how much you're paying attention to this. So UI is like a dial, how much attention you pay to all of these different kinds of exchanges of opinions. The first exchange is the sum of opinions about your own and others on the option that you're evaluating. And then the second sum is about the influence on that option of other agents or yourself, of other options on this option, right? And so for the most generality, we have two different sigmoidal saturation functions here. So remember, I said we're going to saturate opinion exchanges, and that's what S1 and S2 are. But they could be the same saturation function. So the basic idea is that when you have a small attention, this damping term dominates, and the system is going to behave linearly, just like in the exponentially discounted reinforcement learning setting. But when the system is such that you pay attention to this, and because this is a nonlinear term, the systems can behave nonlinearly, and in fact, you can respond with large magnitude. In fact, you can even respond in the opposite direction that your little input told you. So if you're feeling, if you have an input that says, I have a little bias to go this way, your neighbors might push you in the other direction, and they might push you in the other direction with a large magnitude. Okay, so that's kind of messy. So let me just for the rest of this talk, I'm going to just remember that we can. Well, until we get to the end, I'm going to go back to multiple options. But for now, let's just simplify things and talk about the two option case. So I have an opinion about option 1 and an opinion about option 2. And remember, one is relative to the other. So essentially, they sum to 0, right? It's really just, I only need to really keep track of one of them, because I can then, since it's relative to the other, I can compute the opinion about my other option, the other option, as -1 times my opinion about option 1. So I'm just going to use this notation because it's a little bit easier. So xi is just my opinion, agent i's opinion about option 1. And I'm going to set some of these to 0. I'm going to set all the betas and deltas to 0. I'm only going to concentrate on the self-reinforcement and then the straightforward interagent opinion exchange. And so I'm going to redefine A just to be a matrix, the adjacency matrix, unweighted adjacency matrix for interagent network communications. And the magnitude of those weights will be this just common gamma. So AIK tells me, you know, if it's 1, it tells me that I and K are communicating. If it's 0, they're not communicating. So here's what the model looks like in that reduced form. So remember, this is DDT of agent I's opinion about option 1, from which I can compute its opinion about option 2. So when this guy is positive, its opinion about 1 is positive, its opinion about 2 will be negative. So it'll prefer option 1, and when it's ZI1 is negative, it's going to be preferring option 2. So now it looks a lot simpler. Again, you can see we just have this. This is sort of if I ignore this middle term, we see that, exponentially discounted RL model. But now the new term looks like this, where I have this dial, this gain, this attention. I'm saturating, and we use hyperbolic tangent in all the simulations I'm going to show you. This is the self-reinforcing. So if my opinion grows and alpha is positive, it's going to see, I'm going to continue to grow my opinion. And then this is this sum of my neighbor's opinions, and I weight that by this parameter gamma. And then this can be some kind of external stimulus, some input, or it could be some bias that I have. And just a note that this is an odd sigmoidal function. And like I said, we use hyperbolic tangent in all the simulations. Okay, so let me just make a few definitions before I give you some of the fundamental results of the model. So let's let lambda max be the eigenvalue of our adjacency matrix with largest real part, and V max the corresponding unit left eigenvector. Lambda min is the eigenvalue of A, our adjacency matrix with smallest real part, and V min is the corresponding unit left eigenvector of lambda min. Let's let W lambda I be the generalized eigenspace associated to lambda I, an eigenvalue of A. So then I'm going to show you that we can characterize the equilibria as all the equilibria as agreement equilibria or disagreement equilibria, and then we can distinguish when we get agreement, when we get disagreement, as a function of this, the eigenstructure of the adjacency matrix and the parameters like D and alpha and gamma. So an agreement equilibrium is, when I have a non-zero opinion, so distribution of opinion, they're not all zero, and the sign of, so this is, for all my agents, and the sign of agent I's opinion is equal to the sign of agent K's opinion. Okay, for all IK. So we all agree on which option, option 1 or option 2, we prefer. The disagreement equilibria is when at least one pair disagrees. So the sign of, so my preference is the opposite. So the preference of agent I's, the preference of agent I is the opposite of the preference of agent K for at least one pair. So they disagree. Okay, so here's a first result from the paper that I cited earlier, our general model paper. It's a special case of this theorem because we do this for multiple options, and we don't set all those things to 0 that I set to 0, but for this special case where we have just homogeneous alphas and homogeneous D and homogeneous gamma, I'm also going to take homogeneous attention parameter U. I'm going to turn off any bias. Then we get this following result. So just when gamma is positive, remember that was what I defined as cooperative. So influenced in the same direction as you when you're favoring an option, this leads to agreement. And what does that mean? That means that the neutral state, when I'm sort of indifferent between these options, or everybody's indifferent between these options, this is a locally exponentially stable equilibrium when this attention parameter is below a critical value UA, and it's unstable when attention is above this critical value. And that critical value is written as D divided by alpha plus gamma lambda max. So all I need to know is this eigenvector structure of the adjacency matrix, and then these three parameters from the definition of the model. So at this critical point, it's actually a bifurcation. What happens is that the neutral solution becomes unstable, so you no longer stay undecided, and you make a decision, and you make a decision for agreement. So you can get more than one equilibrium here, right? We could all agree on option one. We could all agree on option two. So a steady state bifurcation off of this neutral solution along in the direction of W lambda max, and essentially lambda max, the eigenvector associated with lambda max describes this agreement vector. And then part B, when gamma is negative, remember we define that as competition. So your opinion, you're favoring one option leads me to disfavor that option and therefore favor the other option. In this case, the neutral state again is locally exponentially stable when U is less than a critical, when your attention is lower than some critical threshold. But then the neutral solution becomes unstable when attention is above this critical threshold, and that critical threshold we can also write down very simply. It's the same as above, except instead of looking at the eigenvalue with the largest one, we look at the smallest one. And at this critical point, again, these solutions emerge. So opinion forms. In this case, this is BI is equal to 0. There's no evidence that one option is better than the other. So in some sense, we're already breaking a deadlock. We're making a choice. The branches of disagreement emerge as a steady state bifurcation off of this neutral solution. Again, along this eigen space defined by the minimum eigenvalue, which it turns out to be these disagreement equilibria. Okay, so we do a bit more work. It's actually sort of some non-trivial work to solve for, essentially we can solve for this family of solutions as U changes using something called Lyapunov-Schmidt reduction. And it allows us to draw this conclusion that not only do opinions form as a bifurcation, they form as a pitchfork bifurcation. They form as supercritical pitchfork bifurcations. And the two steady state solutions that emerge are locally exponentially stable, right? So here's the picture. This is the picture in the case of gamma being positive, but you'd see the same picture in the case of gamma being negative. You just interpret the two stable solutions as disagreement as opposed to agreement. But in this case, here is, this is a plot of the solution, which way this group is going. So you can think about this as the inner product of the vector of opinions of all the agents with the eigenvector associated with lambda max, right? That's the space in which the bifurcation is moving along. So this is kind of like a net opinion of the group. So when U is small, so this would be this critical value of U right here is that what we call U sub A. So nothing going, we're just neutral. When we get here, so blue means stable and the red line means unstable. So this neutral solution becomes unstable and these two stable solutions emerge. So this is like everybody agreeing for option one, and this is everybody agreeing for option two. and we get more and more strongly in agreement as U gets larger and larger, and more strongly in agreement for option 2 as U gets larger and larger. And here's just two simulations when U is greater than UA. So somewhere over here, let's say, and gamma is greater than 0. So we're on this agreement picture. And so these are just some random initial conditions. These guys are converging to an agreement state. So this is just, it's actually a kind of a random network. But you get the same story if gamma is less than 0, except now if U is greater than U sub D. So now this critical point is the one computed with lambda min. It's actually for the same initial conditions. All we did was change gamma to be less than 0. Take the same value of U. In this case, the critical values might be slightly different, but as long as we take U greater than both of these, in this case we get a disagreement. So it looks like about half the group goes for option 1 and half the group goes for option 2, and this is as a function of time. So you're looking at sort of convergence to one of these solutions. I mean, this one looks like it's convergence to this solution, and this one, I don't know which one corresponds to this, but this is agreement, half the group for option 1, half the group for option 2, and the other solution is the swap that group picks 2 and this group picks 1. Okay, so that was a case where I had no BIs. Everything was very symmetric and homogeneous. But as soon as you introduce asymmetry, you get what's called an unfolding. And this is something that we can also understand. So you can kind of see when I say unfolding, it means that, you don't have this sort of perfectly symmetric picture, nearby. If there is kind of an asymmetry that leans towards, in this case, option 1, like maybe there's some elements, this is just the vector B of all those inputs or those biases. Maybe some agents are leaning towards option 1. In fact, you can compute which way the group will go by taking the inner product of that vector of inputs or biases with this the eigenvector corresponding to lambda max, right? And if it's positive, so we can prove that the group will agree on option 1, even if some of these B's are negative. But what's kind of interesting is that far away, when U gets really large, there still really is the possibility of the other option if your initial condition is kind of on this side of the unstable solution. So there is this possibility of getting over here. But of course, if you're it depends upon initial conditions. So this is a simulation in which B is actually not 0 on the left, but it happens to be orthogonal to V max, right? So it doesn't affect the symmetry, and we just get essentially we flip a coin when U grows above this critical value. But here we've added to that a component in the direction V max. So with a positive coefficient, so you can see that it pushes this over the curve. And this example is for 3 agents communicating over an undirected line graph. Okay, so that's pretty neat, right? But then you might ask, well, this perimeter U seems super important, and then where does it come from? Like, how do you pick it? And it makes sense, I think, to interpret it as a dynamic variable, right? Something that can change, right? It's a tension. Your tension can change as things in the environment change, or as something happens with your neighbors. Like I think about it, so if we use this model in all kinds of settings, but like in robotics, it could be like like a spatial navigation problem where your tension is grows as you come nearer to, say, to an obstacle or to colliding with another agent. Or in an election, it could be I start listening to U could be really small when the election is a year away, but as I get closer and closer to that day, I start cranking up that dial because I start paying attention to exchanges from others. So it could be some kind of, time urgency or spatial urgency, or just kind of information is starting to leak in. So we actually design feedback dynamics for these attention parameters so that the whole model is self-contained. We're not going to necessarily just exogenously modulate you. So here are the state feedback dynamics that we define, right? So this is just like a little, depending upon what community you come from, it's like a low pass filter or a sort of a leaky integrator if you're from cognitive science and neuroscience. So this is the rate of change of my attention, right? Tau sub u is a time constant, right? So this might be happening more slowly. So SU is another kind of saturating function we're just using here, a Hill activation function, right? So where it was YTH is a threshold that you can choose. And U is like our other parameters, U bar is these are other parameters that bound U. And so what are we doing here inside this is it's like the intensity of the activity of all of the agents that I can measure. So my neighbors and myself. It's sort of how excited we are, how large of an opinion we have. So that it seems kind of natural. Like somebody starts talking to me about the election, so I start paying attention, right? I see, I see, this, something about my neighbors starting to be active in making their opinions. I'm going to start paying attention to this, right? So it's not so much what their opinions are, whether they're for option 1 or for 2, just that they're engaged in the process. I'm going to get engaged and pay attention to them. But this is super interesting, right? This is kind of where we get into this model as providing a means to really explore its responsiveness and its robustness. So how it can distinguish from signals that it should pay attention to and signals that it should reject as disturbance. But essentially what it allows us to do, so I'm sort of skipping a lot of steps here, but we've developed the theory in this newer paper that explains how you could think about this input vector. So its magnitude and its orientation relative to this VC is either Vmax or Vmin, that should say, depending upon, this should say gamma, gamma greater than or less than 0. Whether or not you'll trigger an opinion cascade, for instance. What if only somebody has this inkling that something is going on, and will that be enough, to engage me through these through these DDT, so my attention will grow because somebody has received an input, like they read an article in the newspaper and now they're going to pay attention to what's going on in the election. Their activity grows. Is that enough to bring us all along, the rest of us through the network, to start paying attention to it? And it can be an agreement cascade or a disagreement cascade, right? So I'm showing you here a simulation of an agreement cascade, and you're seeing what's going on with the U's, and a disagreement cascade. I mean, you're seeing what's going on with the U's. Here is what's going on with the opinions. In one case, they go to agreement, and that's because in this dynamic, gamma is positive, right? So here's gamma's +1, and in this whole plot, gamma is -1. In this case, we just pick random inputs random initial conditions. The U's all start at 0, and yet we get this this cascade because somebody here, and it depends upon their location in the network, was or maybe multiple of them were influential enough, and that happens. We can quantify all that in terms of these. You can think about this as as like a centrality measure, like how influential an individual is based on their eigenvector centrality, the component in the left eigenvector associated with lambda max or lambda min, depending upon which of these states or regimes we're in. Okay, so that kind of was meant to give you a little overview, and now I'm going to, in the last few minutes, show you how a model like that, which has a lot of flexibility and yet also a lot of analytic tractability. I mean, granted, I picked a lot of homogeneity in the system, but the idea is that what I showed you in these previous simulations, there was sort of randomness on top of all that homogeneity. So there's some robustness actually nearby that homogeneity. So when all those parameters got perturbed a little bit. But also it gives us a foothold for understanding what happens when you have inhomogeneity or individual differences, like we just saw in these different, distribution of inputs, right? We can start to understand how things that look very symmetric become asymmetric. So let's turn our attention now to thinking about what this means. Back to this, the motivating story, which is the opinion dynamics model in multi-agent strategic interaction. Okay, so I'm replacing the model that we saw before, the exponentially discounted reinforcement learning model, and by adding this new term, right, which is our attention parameter times this a sigmoid. Like a saturation function of this fed back exchanges, either my own agent I's opinion about option J or strategy J, and or weighted by alpha, and or its neighbors' opinions about option J weighted by gamma. Okay, so again, everything else is the same. These would be initial biases of agent I's towards strategy J, and again, we can think about the soft max for picking our distribution, our mixed strategy, and then just to kind of give you a feeling for what's going on here. Let's just suppose, just for a moment, that gamma is equal to alpha, and if I can imagine conditions like maybe, if we're all, the graph is connected and gamma is positive or equal to alpha, and it grows, right? We all come to agreement. And if gamma gets really, really large, the saturation function just is going to saturate at 1, right? In that case, we can look at what the equilibrium looks like, right? So the equilibrium kind of looks like, instead of just being the payoff at the equilibrium, you can kind of see what's going on here in this kind of limiting case, that you have this opportunity in this model of getting a steady state solution where you add the U or you subtract the U, depending upon whether it's, you're going to this positive or this negative state. So I hope that makes sense. I just want to give you a feeling for how in the context of strategic interactions we get to payoffs that have different value, that they can grow or get smaller than the nominal payoff matrix. Okay, so let me now talk about this in the context of, I'm going to talk about 2 games. And the first is the prisoner's dilemma. The other one will be the traveler's dilemma. It's like, I think they're just kind of, it's very interesting. It also just kind of, gives you these ideas, but I and my colleagues welcome your your ideas and feedback and even possible collaborations, because we think this is kind of exciting, and we hope it strikes you so as well. So let's think about the prisoner's dilemma. Let's just think about two agent prisoner's dilemma. So each agent has two possible strategies. They can cooperate, they can defect. And let's use the softmax to get our mixed strategy. Okay, and I'm just setting temperature equal to 1, so 8 is equal to 1. So the probability that agent I selects strategy J, so either cooperate or defect, it looks like this, right? So it's just based on those scores, right? So that's agent I's score for if J is equal to 1, right? You could write it like this. So this tells me, how I distribute my probability among the two options based upon my two scores. And then the reward that agent gets for selecting the strategies is going to, just depend upon this payoff matrix, which will depend upon all of the other strategies of the other guy. So that's our interaction. So what does this model look like in this context? Okay, so I'm going to set alpha equal to 0. We won't do any self-reinforcing. We only have two agents. So here, what we're doing, that agent 1, this is agent 1, the rate of change of its score for strategy 1, which is cooperate, strategy 2, which is defect, looks like, we've got these two terms, which are precisely the exponentially discounted reinforcement learning model, but now we have this extra term, right, which has this dial U hyperbolic tangent of the communicated, this is the relative score that agent 2 has about option 1, agent 2 has about option 2. And this is completely analogous. Agent 2 is taking account of agent 1's, what they've been communicated about agent 1, opinion about option 1 and about option 2. Okay, so this is the idea. So we're looking at prisoner's dilemma, but now there's some crosstalk. We're sharing our opinions about these options. And so then this is just a standard payoff matrix in the prisoner's dilemma. Remember, option 1 is to cooperate, option 2 is to defect. Okay, so this is the reward that agent 1 gets as a function of agent 2's mixed strategy, and this is the reward that agent 2 gets as a function of agent 1's mixed strategy. And so this is what happens with our model, right? So in the when U is just small, not much going on, you get the Nash equilibrium, which is that both agents are going to defect. So let me just show you what we're plotting here. So we've used D is equal to 1, U is small, gamma is equal to 1, although U is small, so there's not a lot of exchange taking place, but this would be, kind of like I'm looking at their opinions, and I'm drawn to their opinions. And so this is initial conditions for agent 1, right? This is my opinions of option 1, option 2, and now this, which is plotted with the color scale, is the probability that agent 1 cooperates minus the probability that agent 1 defects, and you can see that it's very negative. So this is the defecting for all initial conditions, and this is agent 2 defecting for all initial conditions. So this is the Nash equilibrium. Both agents defect. Okay, so but now what happens if we crank up our attention to this communicated scores from our neighbors? Whoops. And this is what happens, right? So I'm showing you this picture here because we were way down here where this exchange wasn't playing into anything much. Now we're way over here because we've taken U to be equal to 3. So we're right here on this pitchfork bifurcation. So you can see that this is a stable solution for defecting, and this is a stable solution for cooperating. In fact, as I crank up U, I'll defect more, but then, at some point for some critical value, I'm going to start for some initial conditions, I'm going to start creating this opportunity to cooperate. And this is just a particular choice where you can see that there's a whole bunch of initial conditions, this whole region that's bright red for all these initial conditions, which granted is, an initial bias towards cooperating, right? That's what these are. But for all these initial conditions, we get a second equilibrium that's stable in addition to the Nash equilibrium. And so under these conditions, the two agents will cooperate. Okay, so that's, the beginning of the story, right? But we also talked about the fact that, well, it's sort of arbitrary for you just to be this static number. Where does it come from? So here's an idea that Shinku had about how to design some dynamics for this attention. Like when would you want to pay attention to your neighbor, right? So, well, you'd want to pay attention to your neighbor when you had the idea that what they were doing was really good, right? So how would you measure that? Well, that would be, you take their, the inner product of their mixed strategy with your rewards. So if you were doing what they were doing, this would be your reward. And if that's big, I mean, we're saturating it, but if that's big, and this tan hyperbolic tangent +1 just brings us into the 0 to 1 as opposed to -1 to 1, which is what hyperbolic tangent is. If that's big, then I'm going to grow my attention, right? If I think that if I were doing what they're doing is going to give me more reward, I should pay more attention to what they're doing in this whole process. And, the other guy is going to do the same thing. Okay, so this is super interesting. So you think, well, that should help, right? It should grow my U, right? But you could also worry, but if we're stuck at this Nash equilibrium, right? How are we going to get away from that, right? We're both kind of defecting, which isn't really giving us a very high payoff, right? And so, it turns out that so this is another interesting twist. So if we use the standard payoff matrix, let me just show you what happens in this case. Like the first idea, we start the U's off at 0 because there's no reason to be paying attention, and then they grow. But we don't get very far. We don't get very far. In fact, I probably should have drawn this a little further to. No, yeah, it's a little. Yeah, no, it's further to the left, so it's less strongly defecting, but we're still defecting, so nothing much happened, right? So here's an interesting idea. If you take the same payoff matrix and you add 1 to every element, you still get the prisoner's dilemma. But in some sense, what we've done is introduce a change in the framing. So this whole idea that when things are, everything up till now has been about sort of relative payoffs, but now where it's kind of, we've done this thing where now we're kind of looking at absolute payoffs and having that drive our dynamics. And if this is framed in terms of I'm penalized less as opposed, nothing happened. But as soon as we add to this, and we now are starting to see some positive rewards. So instead of being penalized less, I frame this in terms of I'm actually going to get a reward, not just less prison time, but somebody's going to give me some nice reward. The framing problem, I actually respond to that. So now my U does grow, and it grows large enough. Whoopsie, I went the wrong way. Sorry. So that even though we started at 0, the U's both grow so that cooperate. Maybe not, at this point for those parameters, it didn't grow as high as it was before, but there is still this region in which we region of attraction for this other solution to cooperate, which is pretty neat, right? So I mean, the only difference was the framing, like that the fact that we were getting positive reward. So that's my first example, and then sorry, it's kind of jumpy. Let's talk about the traveler's dilemma, and then I'll stop. So let's talk about the two-agent traveler's dilemma. And actually, this is kind of nice because it's an example in which we have more than two strategies. And so the model that I just described to you in its fuller form, where we have multiple options, comes into play. So you might remember the traveler's dilemma. This is like two travelers arrive at the airport. Their bags, which are identical and have identical kind of valuables in them, are lost, and the airline asks them to bid on, how much money it's worth, so that they'll get that money recovered. But it's a little bit of a game, in that you want to be the lower bidder, because the lowball offer, giving the lowball offer is better to you. So it goes like this. So the way we set this up, sort of have like a discrete number of strategies. So you can bid, in this case, strategy J is to bid $101 minus J. So when J is equal to 1, that says you're bidding $100. When J is equal to 2, you're bidding $99, etc. Okay, so basically you can bid from $100 all the way down to $2. Then again, we use the softmax to compute your strategy among those 99 options, 99 strategies. But then here is how the reward works. So if agent I, 1 or 2, selects strategy J sub I, and agent K selects strategy J sub K, and suppose Ji is greater than Jk, so Ji is lowering their bid more than agent K is, so agent I has made the lower bid, then agent I gets $100 minus, they get their bid, plus $2, and agent K gets agent I's bid minus $2, gets penalized. Okay, so what's weird is that the Nash equilibrium is that both agents should bid $2, sort of the minimum that they could possibly get. And so I'll show you a little dynamic where we recover that, but also show a little change to the dynamic. So if you just do the sort of exponentially discounted learning, and you ignore the term in the middle, you're going to get the $2. But what we add here is so now I've set gamma equal to 0, and we've just introduced this alpha. So remember the alpha term, that's self-reinforcing. That's like staying strong. That's like, sticking to your guns on your opinions about what you'd like to get out of this sort of bidding war. And so it's just here, you don't even need to know what the other guy is, has what their opinion is, right? Because they do the same thing with their own opinion. And so here's what the reward matrix looks like. This is exactly what I just described. You get, if you say the same thing, if you both say, $100, then you both get $100. But if you're the lower bidder, like if you say 99 and they say, if you say 100 and they say 99, you get 97, et cetera. So here's the big reward matrix. And let me show you what happens. So here is the example when U is equal to 0. And what I'm showing you here is agent I. This could be 1 or 2. They're going to be identical for picking strategies J. And we're showing you, oh, shoot. Shoot. I neglected to use the up-to-date pictures, which should show you that the $2 solution is the one that comes out ahead. Sorry about that. as you crank up U, you can see that the solution, and this is for, you can kind of see what the initial conditions look like. The solution, cranking up U a little bit, is that you get the sort of highest opinion about choosing $20. If I go even higher, $40, and even higher on my U, I'm sorry. This is my opinion of $100 and some of the other higher numbers, because those are in red. But now my opinion, when I'm really cranking up my gain, when I'm really sort of doing this self-reinforcing, is that kind of, my opinion about bidding $100 completely overwhelms my other opinions. And everybody, both agents do this. And so that's really nice, because there's a high probability that we'll both choose $100 and we'll both get $100, as opposed to being stuck in this case where $2, not plotted here, but $2 ends up having the highest probability, which is the Nash equilibrium. So let me conclude. So the summary statement is that we have extended this framework called exponentially discounted reinforcement learning for multi-agent games, is finite multi-agent games and continuous time, to an opinion dynamics learning for multi-agent finite games and continuous time. And importantly, in this opinion dynamics model, opinions form through a bifurcation, which yields this multi-stability of network opinion configurations. And that sort of leads to all the richness that we just explored a little bit, opening up the, what we think are new possibilities and new questions. So in the prisoner's dilemma, we saw that cooperation and defection both became stable solutions, not just defection, when we introduce a little bit of communicating of opinions. And then this introduction of like dynamics on attention suggests possibly that within this model, this idea of framing, we can explore that. Lots of interesting possibilities, of course, to extend to multiple agents, to look at the role of network structure in this sort of multi-agent prisoner's dilemma story. Likewise, we just looked at the traveler's dilemma with this idea of introducing self-reinforcement of opinions. And as that grows, the higher bids become more likely. So with that, I will just say thank you for listening. I want to thank my research group, my family, and my funders. Thanks very much.
Thank you, Naomi. It was a very interesting talk. And now I unmute, the audience can unmute themselves and ask a question. And there are several questions in the chat, and your PhD student answered some of them. Maybe if they want, for example, Ji Liu or Shankaranayanan. If you want to ask that question, you can unmute and ask, or I can just relay for you as well.
Should I stop share? Let's see, because I can't. Oh, I can see the chat. All right. Do you want me to stop share?
Thank you. I would have it clarified by already your master students. Thank you for the time.
Oh, okay.
Okay.
Oh, thank you, Anastasia.
Yeah, there was another question by Ji Liu. He asked, is graph being undirected critical for these results? Does the model have same or similar behavior for a directed, strongly connected graph?
Yeah, so we do have a bunch of results for directed graphs. Yeah, I mean, it's just easier to present this. Those are harder results, but we do have some and interesting ones. Yeah, I mean, you can get you can get all kinds of things. You can get non-simple eigenvalues, and then you can get other kinds of solutions. You can even get periodic solutions. Really interesting things can happen.
Okay. I have a quick question. Do you find those results counterintuitive or intuitive, like from a high-level interpretation?
You mean these last results and these examples? Well, certainly the traveler's dilemma seems kind of intuitive, doesn't it? Right, that you would you put more, essentially more confidence in your interest in the higher bid with the self-reinforcing. I think in the other case, yeah, I think it's also it does seem intuitive, right? That if I mean, we kind of, unfortunately, we use the word cooperate twice, right? Because we're using it in the context of the model. But the positive gamma, the fact that I'm listening a little bit in on what the other, I'm sharing with my neighbors at least what their opinions are, means that I'm going to go kind of along with them. And yeah, I mean, it does somehow seem intuitive. You could imagine though, but then you're just going to agree on defecting, right? But it's that it's not that you're not going to agree on defecting. It depends upon your initial conditions. So if we both have this bias, like you saw that, like the red stuff was coming at the top, that was when we have our initial conditions sort of towards cooperate. So that kind of makes sense, right? So if you and I are both kind of initially hoping we can cooperate, but we don't talk to each other at all, we end up defecting, right?
Okay.
But if we both have this bias and then we start like, oh yeah, and then we'll you want to cooperate? Yeah, okay, I want to go. You're leaning that way. I'm going to lean that way. It does seem. And then the dynamic version of that, I think I described it, the sort of intuition behind it. Yeah.
Now, Naomi, given that the dynamics exhibit some bifurcation,
Yeah.
this would be open to manipulation by an external agent or external source. As we know, this happens all the time. So have you looked into that robustness sort of aspects of these opinion dynamics models and what an adversarial input, the extent to which an adversarial input would move it toward either one sort of a dynamics at the bifurcation point or another?
Yeah, I mean, we've definitely looked at it just sort of systematically as opposed to thinking of it as an adversary. But so we do know, like the stuff I was telling you about, these sort of centrality indices, and then we can see who comes in where. But we haven't looked at it sort of as an adversary. So if it's being driven by a utility function, how might it mess up the game?
Like to deceive some
to be deliberate. Like we would know how to do it if we were kind of all knowing, looking at this, and there wasn't, we weren't really thinking about, somebody reacting strategically. But I guess the answer is like we know in principle. We haven't looked at it in the context of strategic, but that would be super interesting to look at.
There's one more final question at the chat. Grant
Okay.
Empirically, it seems like in the Travel's dilemma, the agents would play something in the 90s, not 100, but not too far off. Though this is in the one round case, are there empirical results for the repeated case? Can your results recover these results? Or if you were Grant, you can also unmute yourself and ask the question verbally.
Yeah, by high 90s, I mean the reported price. I think you inverted the strategies, but so.
I'm sorry, I'm not sure the question.
So the question is, empirically, if you run a one-shot game of the Traveler's Dilemma, which is really just a model of a repeated prisoner's dilemma, right? You get that people will kind of report a price in the high 90s, typically.
Right. Okay.
90s, and so, but I don't know what happens in a repeated Traveler's game if this has been run empirically, and it seems like your results have people cooperating at 100. So I'm wondering if your model can recover the empirical result that happened.
Well, the empirical result. So, I mean so as I understand it, the Nash equilibrium is that they, repeatedly they'll they'll go to $2, right? If you play this.
Right. So I'm
repeatedly.
talking about like if you just run it in the lab, like with real people.
Oh no.
Not the Nash equilibrium, because that's no one plays that, right? That's
I don't know. Yeah. So you're saying that if you run in the lab, you don't get to $2, you get to something in the high 90s.
I don't, for the one shot, I know you get stuff in the 90s. I don't know what happens when you run it repeatedly in the lab. I'm not aware of those results. I was wondering if you knew.
Oh, okay. Yeah, I don't know. I don't know. It'd be super interesting to see what people have found. Yeah, because if you look at our, what have I done here? I can't, let me just, okay. I was going to say, if you look at our, I can't see. All right. Somehow I can't. Oh, okay. All right. Sorry. Oh, I mean, because if you look at, I mean, you can, you'd see the one shot. Oh gosh. Here, let me go this way. Right. So here, I get, at the beginning, you're way up here. So this is probably what you're seeing. Like this is a high opinion for high numbers, just over a little bit of time, right? So it takes some time, right, to converge, right? I mean, this is presumably a lot of iterations, right? So I would guess that maybe, I don't know if you see in the lab that if you keep doing it, that it declines.
Yeah, I don't know either.
That's an interesting question. Thank you.
Thank you very much for your attention, and thank you very much, Naomi, again. It was an excellent talk, and yeah, thank you.
Great, thank you.